Okay, let's run through some examples. Example number 1, f of x is defined to be 3x squared minus 2, and that is defined on the interval -1 to 2. For part A, we want to find the average rate of change, specifically the average rate of change on the interval -1 to 2. And so we know we've represented the average rate of change as the slope of that secant line, or the change in y over change in x. So that's going to be f of 2 minus f of -1 all over the 2 minus the -1. Okay, so f of 2, we have to plug in 2 into our function, and that's going to be 3 times 4 minus 2. And then we have to subtract the f of -1, so f of -1 is going to be 3 minus 2, and that's going to be all over 3, coming out to be 9 over 3, simplifies to be 3. That is the average rate of change on the interval -1 to 2. Now for part B, we want to find the instantaneous rate of change at x equals 1. Remember, instantaneous rate of change is the same thing as the slope at x equals 1, which is the same thing as the derivative at x equals 1. And we're going to use this Lagrange notation, f prime of 1. Remember, that says all three of those things. That's the slope at 1, that's the instantaneous rate of change at 1, that is the derivative at 1. And we could even throw in there that that is the slope of the tangent at x equals 1. Okay, so in order to do this using the definition, we'll use the standard definition, which is the limit as h goes to 0. I want to emphasize that this is not the limit when we did continuity. This is the limit of the difference quotient. It's a much different limit. So this is the limit h goes to 0, f of 1 plus h. See, before we kept calling this a. In this case, the a is a 1. So this is the limit as h goes to 0, f of 1 plus h minus f of 1. Please avoid the temptation to use x plus h as described earlier. All right. Once we have that, and I do want to see that because this gives us what we're working with. This is the concept. Now we're going to find the limit as h goes to 0. When I plug 1 plus h into my function, I'll get this expression. Okay, and then when I plug 1 into the function, I get 3 minus 2. I'm purposely leaving that unsimplified, all over h. And the way we find this limit is the same way we found limits in the earlier section. It's a different limit that we're finding, but the method to find a limit doesn't change. So this is the limit as h approaches 0. Now I'm going to expand or FOIL this and then distribute the 3 at the same time. So this is going to give me 3 plus 6h plus h squared, and then I have minus 2. All of that minus 1 all over h. Now, a beautiful thing happens here. We will notice that constants will cancel. 3 minus 2 minus 1 goes to 0. So that makes me happy. And so now we're left with the limit as h goes to 0. Once those numbers cancel out, you might see that we can factor an h out of the numerator, which gives me 6 plus h over h. And we have the nice quality of simplification here. It's not enough to just cross those out. As we talked about earlier, I would like to see the result after simplification. So that leaves me to 6 plus h. The limit as h goes to 0. And that clearly, through substitution, is equal to 6. And this tells me that f has a derivative, or we can say has a slope, at x equals 1. It does have a value. The slope is 6. And so this slope that I am referring to at x equals 1, this slope is equal to 6. In part C, we are asked to write an equation of the line tangent to the function at x equals 1. We're writing the equation of that blue tangent line that we drew earlier. We want an equation of the line. I would like to review something here. I would like to review point slope form. And point slope form is y minus y1 equals m x minus x1. This is called point slope form because we have the slope, but we also have the point x1 comma y1. Now I'm going to be a little bit more fancy than this. This comes out to be y minus, instead of y1, I'll say f at some value a. And then instead of the slope, we will represent the slope as f prime of a, which we've been discussing. And then x minus the x value is a. So this here is just a fancier way of doing point slope form. And so this tells me this is the general, and what I need specifically would be y minus f at 1 equals f prime at 1 x minus 1. This would be specific to this particular problem. So in this particular problem, I'm going to need f of 1. And if I find f of 1, that was 1 squared minus 2. That's just plugging into the function. That comes out to be 1. I will also need the slope at 1, which we showed as f prime of 1, and that's what we computed to be 6. So if I plug those elements into my equation, point slope form, this is going to be y minus 1 equals 6 x minus 1. And there we have an equation of the tangent line to the function. There are different ways to write this. You could make this y equals by adding 1 to both sides. You could simplify it, but you are not required. I kind of like keeping it in this form because this becomes a good form to use in the future. Okay, let's turn to page example number 2. F of x is the square root of x plus 1 on the interval 0 to 8. We want to talk about the average rate of change on the interval 0 to 8 in part A. Let's do this a little quicker. We need f of 8 minus f of 0 all over 8 minus 0. That's the change in y over the change in x. So this gives us the square root of 9 minus the square root of 1 over 8. And this comes out to be 2/8, or simplified to be 1/4. That is the average rate of change. I think it's worth drawing a picture of this function here. If we were to graph the square root of x plus 1, it's going to be this. Let me change the color. This is going to be some swooshy shape that looks like this. And if I'm trying to find the average rate of change from x equals 0 to x equals 8, then I could draw a secant line connecting those two, and then using rise over run or change in y over change in x, I computed the slope to be 1/4. Now to find the instantaneous rate of change of f at x equals 3, or the slope at 3, we're going to use f prime of 3. And this time, just to change it up here, I'm going to use the alternate definition. This is going to be the limit as alternate. Find that alternate definition. I'm going to find this. All right. So this is going to be, instead of h goes to 0, this is going to be x goes to 3 using this alternate definition. And this time we have f of x minus f of 3 all over x minus 3. This is the alternate difference quotient, and then the limit of the difference quotient gives us the alternate definition. All right, let's keep going with this. So we have the limit as x goes to 3. This is going to give me the square root of x plus 1 minus 2 all over x minus 3. And this leads us to a very familiar spot. We need to find the limit, and we certainly cannot plug 3 in because we would be dividing by 0. So we're going to employ our good old algebra skills. This is the limit as x goes to 3. I'm going to multiply the top and bottom by the conjugate of the numerator. I'm showing it here in blue, but I don't have to show that step. The thing I am going to show is the result after I expand that out. So the numerator is going to read x plus 1 minus 4, and the denominator, if you recall, we leave alone here. All right, be patient with me. Okay, good. I hope that you can see now that the numerator becomes x minus 3, which cancels with the denominator. So I'm going to show the result of that simplification. And it gives us 1 over the square root of x plus 1 plus 2. Now I can substitute it in, and it comes out to be 1/4. Whoa! 1/4. Is this a coincidence? Oh boy, it's hard to answer that question. I'm going to say yes, no, maybe so. Is that a coincidence? Well, in order for you to understand my neuroses, let's talk about it. If I found the slope at 1 here, then my tangent line would look like this, and the slope would certainly be larger than the slope of the segment in red. So it certainly would be something different than a fourth. If I picked a tangent line real close to 8, then that slope is certainly, I drew that terribly, but that slope is certainly smaller than the segment in red. So it turns out that I just so happened to pick a point, and that point would be 1, 2, 3. I just so happened to pick a point where the slope of the tangent is equal to the slope of the secant. See, when I draw this tangent line here, they're supposed to be parallel, and they have the same slope. Any other point other than asking you at 3 would have given me a different value than 1/4. And I chose to pick 3, and then these slopes came out to be identical. The instantaneous was equal to the average, and that, I suppose, is coincidence. Big picture-wise, this tells us that f has a derivative. F has a derivative, or f has a slope at x equals 3. And that slope is equal to 1/4. Part C, equation of the tangent line. I'm going to write this, I can't help it. Y minus f at 3 equals f prime of 3, x minus 3. That's our point slope form. So we certainly need f of 3, and we are going to need f prime of 3. F prime of 3 we just found to be a fourth. That was the slope. And f of 3, if I plug 3 into the original function, that comes out to be 4. So our equation is y minus 4 equals 1/4 times the quantity x minus 3. And I'll put a box around that guy. Example number 3 is a piecewise function, as seen here, also seen in your notes, defined on 0 to 2. I want to make one observation that f of 1, well, would I plug the 1 into the top or the bottom? Clearly, I'm going to plug it into the top because that's where it's equal, and that comes out to be 3. I'm going to draw upon that later. Part A, average rate of change on 0 to 2. F of 2 minus f of 0 all over 2 minus 0. F of 2, well, we have to plug the 2 into the top, and that's going to be 5 minus 4. And 0, we have to plug into the bottom, and that's going to be equal to 6, and that's all over 2. Okie dokie. And so that average rate of change of this piecewise function is negative 2/5. Part B, instantaneous rate of change, slope at 1. F prime of 1 equals the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. And here's where we have, I guess I'll call it a problem. This is a piecewise function of the difference quotient. The behavior is different to the right or left of 1, so we can't directly find this limit, and so we will need 2 one-sided limits of this difference quotient. So the first one, I'm purposely leaving a little bit of space here because I want to write something when we're done doing this one-sided limit. We need the limit as h approaches 0 from the right. That's delta x is getting smaller to the right of 1, so 0 is, so we're getting close to 0 in positive numbers. Okay, so this is going to be the limit as h approaches 0 from the right of f of 1 plus h minus f of 1 all over h, which equals the limit as h approaches 0 from the right. Now, f of 1 plus h, where h is positive but getting close to 0. Since h is positive, we're to the right of 1, so the behavior of the function is the top. 5 minus 2 times 1 plus h minus f of 1. I had said earlier, f of 1, no matter what we say, f of 1 we computed to be equal to 3. That was the 5 minus 2. That came out to be equal to 3. And this, of course, is going to be all over h. Now, with a little simplification, let's keep going. This is the limit as h goes to 0 from the right of, the top is going to be negative 2h, the bottom is h. It's not enough to cancel those out, so I'm going to cancel those out first. See, I can't plug 0 in, so I have to get it to a place where I can plug. Now there's nothing to plug, and the limit of a constant is simply the constant. Okay, so we could say almost that the slope from the right is equal to negative 2, if you're comfortable with that terminology. Now for some notation, we left a space over here. We're going to call this f prime at 1, but I'm going to put a little plus down here, meaning it's the slope as we approach from the right. It's the limit of this difference quotient as we approach from the positive side or from the right-hand side. So you won't find this notation in your book, but it is a little fancy, and it's kind of convenient because it's very descriptive of what we're doing. So since we found the limit from the right, we now have to find the limit from the left, and I'm going to say f prime of 1 from the left, which is the limit as h approaches 0 from the left. See, since h is approaching 0 from the left, we're talking about negative small h values. And so when I say f of 1 plus h minus f of 1 all over h, when I say the 1 plus h, that actually is 1 minus some small number, so that's going to bring my behavior to the left of 1. And so when I plug 1 plus h, I'm going to plug that in to the bottom part of this piecewise function. So that's going to be 6 minus 4 times 1 plus h plus 1 plus h squared. And then we're going to subtract. I'm going to use this blue color again to emphasize that this part here, the f of 1, doesn't change. That's going to be the 5 minus 2, and now we can see that visually. And of course, this is all over h. And I can't help myself. I want to take the moment now to expand all this out and write what it looks like. So this, the limit as h goes to 0. We have the 6 minus 4 minus 4h plus 1 plus 2h plus h squared. And then we have that minus 3 tailing off at the end. All over h. Okay, what does this simplify to be? Well, we have the limit as h goes to 0 from the left. This is going to be h, negative 2 plus h over h. I want to show that simplification. So this is the limit as h goes to 0 from the left, negative 2 plus h. This allows me to substitute in, and I get negative 2. All right, and I'm actually pretty happy that I got a negative 2. See, when we found the slope from the right, it was negative 2. And when we find the slope from the left, it's also equal to negative 2. So that tells me that the slope will be negative 2. If these numbers were different, let's say this was negative 2 and this was 5, well, then that would be a sharp transition, and then we wouldn't have a slope. Okay, I'm getting a little bit ahead of myself. So what I want to do here is, see, I found this limit here. The limit as h approaches 0, and I found the limit as h approaches 0 from the left. And so locally, what I want to conclude, and I'm going to put that here locally, is that the limit as h approaches 0 period of f of 1 plus h minus f of 1 all over h, that is equal to negative 2. The limit from the right equaled the limit from the left, so the limit of this difference quotient is equal to negative 2. And I'm going to say i.e., or that is, f prime of 1 equals negative 2. And we'll note that f does have a derivative or a slope at x equals 1, and this slope is equal to negative 2. Back to that sharp corner. Again, these two numbers are the same, so the slope as we approach from the right is negative 2, and the slope as we approach from the left is negative 2. And so we would say here that there is a smooth transition. So if a function has a smooth transition, it will have a slope, it will have a derivative, and we say it's differentiable at x equals 1 because of that smooth transition. Okay, finally part C, we will need two elements. We're going to need f of 1 equals 3, and we're going to need the slope f prime of 1, which we found to be negative 2. We piece it together. Y minus 3 equals negative 2 x minus 1. That is the equation of the tangent line to that function with a smooth transition at x equals negative 2. Okay, example 4 is also a piecewise function. This time we're looking at the function g of x on the interval negative 2 to 5. Let's do part A and let's do it fast. The average rate of change on that interval negative 2 to 5 is going to be g of 5 minus g of negative 2 all over 5 minus negative 2. This is going to come out to be, I plug 5 into the top function, gives me 0. I plug negative 2 into the bottom function, that gives me 1. This is all over 7, and so the average rate of change is negative 1/7. I now want to find g prime at 0, which is the limit as h goes to 0 of g of 0 plus h minus g of 0 all over h. And we run into this piecewise problem again where the behavior to the right of 0 is different from the behavior to the left. So before I find this answer, I've got to do two one-sided limits. We'll first find the slope as we approach from the right using this g prime of 0 from the right notation. So that's going to be the limit as h approaches 0 from the right, meaning h is small but positive, and we write this generic 0 plus h. 0 plus h will bring us to the right of 0 minus g of 0 all over h. Okay, so that's going to be the limit. H goes to 0. We plug the 0 plus h into the top because we're to the right of 0. So we have 5 minus 0 plus h minus, I'll use this blue business again, because when I plug 0 in, that doesn't change. It's going to be 5 minus 0. That blue part always gets plugged into the top all over h. Okay, so this is the limit as h approaches 0 from the right of, it looks like we have negative h over h. We want to simplify the limit as h goes to 0 from the right of negative 1. Limit of a constant is a constant. So this is telling me the slope as we approach from the right, the slope is equal to negative 1. That's the slope from the right-hand side. But now we have to find the slope from the left-hand side. Okay, and this is going to be the limit as h approaches 0 from the left. We got to write this even though it's somewhat of a pain in the neck. I would appreciate you writing this over h, which equals the limit as h approaches 0 from the left. H is approaching 0 from the left. Small negative means the behavior is to the left of 0. So we've got to plug this into the bottom part of our piecewise function. I'll use the blue because this part doesn't change. G of 0 is always 5 minus 0 all over h, giving us the limit as h goes to 0 from the left of, this time, 2h over h, which is the limit as h approaches 0 from the left. Simplifies to 2, and then the limit of a constant is the constant. So the slope as we approach from the right-hand side is 2. And I think you may see the issue here. The slope from the right was negative 1. The slope from the left was 2. Those are different. So what happened? Looks like a sharp transition to me, means there is no slope, and I keep getting ahead of myself. Locally, what have we concluded? The limit from the right was equal to something. The limit from the left was equal to something different. And therefore, the limit as h approaches 0 of g of 0 plus h minus g of 0 all over h does not exist. G prime of 0 does not exist. G does not have a derivative. It does not have a slope at x equals 0. We could say that G is not differentiable, derivative differentiable at x equals 0. No derivative, no slope, sharp transition. We have a corner at x equals 0. Quick shape, quick drawing, and I mean quick. To the left had a slope of 2. So we see the approach is 2 from the left, and from the right the slope was -1. Sharp transition, corner. In part C, it wants us to write an equation of the tangent line, but guess what? We don't have a tangent line. So G does not have a unique, or simply does not have a tangent line at x equals 0. So I can't write its equation because there is not one. Or at least there's not a unique one, and so we say there is not one.